In the first lesson in Unit 2, you learned how to add the motor command. You set motor power to make the wheels move, and a positive value for the power would move those wheels clockwise, while a negative value would move them counterclockwise. It's important to note that the robot is moving forward when it's moving in this direction. So we have our robot brain at the rear of the robot. For your robot to move forward then, we learned that the right motor actually has to go counterclockwise, or a negative value on power, in order for that motor to move forward. And then the left motor would move clockwise. Entering the wait command is what told the program how long it should run those motors. In the second lesson, set motor time command was introduced, where you were able to set additional parameters instead of just set motor power with the parameters of identifying which motor and then giving it its speed using percent power. You also could include the number of seconds it should run, and then whether the wait until finish is a true or false statement in this case. Let's take a look at an example. So here we have the same program as was mentioned earlier in this video using set motor power, but this time with set motor time. Notice that we don't need the wait command because now the wait is part of the set of parameters. So if I click on set motor time here, I can see where the parameters can be entered, and I have my percent power the same, but right here I can say for 5 seconds and wait until finish is true. We learned, however, that the first motor, wait until finish, had to be set to false so that it wouldn't run this motor and wait the 5 seconds before it ran this one, which would turn it one direction in circles and then the other direction in circles. So the first one is set to false so that it runs both of these commands at the same time. In final summary, here again we have these two programs that run exactly the same thing. This one, we used the wait command in between and then stopped the motor. And this one, we used the set motor time control to have all of the parameters together. And again, noted that there was no wait. This one was false in order for the next line to be read at the same time. When we use time in relationship to our programming, we're telling the robot how long it should travel. But it's more useful, most often, to tell the model how far we want it to travel. In that case, we use rotations. So in this lesson, you're going to learn how to use the motor rotation control. Now, in this case, where we're defining the distance we want the robot to travel, we're using set motor rotations. So the first parameter when we open or set our motor rotation is still to identify which motor and then set the power, so clockwise, or if it's negative, counterclockwise. But now instead of time, we have a distance value. Here it says you can set the number of rotations. The value of this parameter defines how many times the wheels should turn. You can also specify parts of rotations. So setting rotations to 1.5 will rotate the wheel 1.5 times. And then finally, our wait until finish. Do you want this command line to wait until it finishes before going to the next command line? Or do you want it to go ahead and go to the next command line? And we learned that in order for both wheels to be running the command line at the same time, the first one in our program has to be false while the second one is true. Let's do this activity. Each time the wheel motor rotates once, the wheel itself will rotate exactly once. The more rotations the wheels turn, the further the model will move. Well, of course, right? If the wheel was bigger, the model would move further each time the motor turned the wheel around once. True. To know how many motor rotations are required to travel a specific distance, we must first find out what distance one rotation travels. We can find this out by calculating the circumference of the wheel. So we have the diameter in relationship to the circumference of the wheel. The circumference is calculated as circumference equals pi times diameter. Pi is a Greek letter that represents the number 3.14159, and it goes on. So if we have the diameter of a circle, we can multiply it by 3.14 to calculate the circumference of the circle. Measure the diameter of your model's wheel using a ruler. You should find that the wheel's diameter is 2.5 inches. We saw earlier that the circumference of a circle is calculated as follows. Since the diameter of the model's wheel is 2.5 inches, the wheel's circumference is calculated as follows. The circumference would be 3.14 times 2.5 inches. So their circumference is 7.9 inches. To make it simpler for today, let's consider the wheel's circumference to be 8 inches. To confirm this, align the front wheel of your model next to the start of a piece of paper. Mark a point on the side of the front wheel where it meets the paper. Move your model forward so that the wheel rotates one single rotation and the marked point touches the paper again. Mark a point on the paper where the point of the wheel meets the paper and then measure that length. And there it is, about 8 inches. Students wrote the program to test it out, one full rotation, just exactly what you saw in the video, and ran it. Measured the distance, and indeed, they should have found it was 8 inches. In slide 16, then, we were to choose the answer that would allow the model to move backwards around 4 inches. So if one full rotation goes 8 inches, then backward, or 4 inches would be half of a rotation, and backwards would be the opposite of our original program where the right motor had a negative value and the left motor had positive. So right motor is going to have positive value, left motor negative. So it would be this one, except we should have a true value on this second line, command line. Otherwise, both of these are ignored and the program ends. But this is intended to be the correct one. A recap. Your model can be instructed to move according to a number of motor rotations using the set motor rotations command. Each motor rotation results in your model moving 8 inches. Using this information, you can construct or instruct your model to move a specific distance. Convert 3 feet to inches. So we have 12 inches. Let's instruct your model to move forward 3 feet. So we need 36 inches. Well, how many rotations would that be? We need to know how many times 8 inches will go into those 36 inches because each rotation is 8 inches. So here, 36 divided by 8 is 4.5. We need 4.5 rotations. So when we set our motor rotations, we have the right motor going forward, so negative 100 on the right motor, 4.5 seconds. Wait until finish false because we need this one to to run this command line to run simultaneously. So left motor at 100, 4.5 rotations, and this time wait until finish is true. So when we run that program, it should go 3 feet. So you learned in this lesson how to set motor rotations in order to have the robot move a specific distance. In order to do that, we had to determine the length of one wheel rotation, which is the same as its circumference, and use that information within the command line.